Welcome back. So we're working on an exercise involving linear programming. And what we want to do is we want to find the values for x and y that will maximize this equation, this cost equation, if you will, given these certain constraints. We started off by graphing these three constraints on the graph, and we actually found 3 points around the feasibility region where one of these 3 points will give the maximum and minimum values for this given equation. So what we're going to do now is we're going to find these 3 points using these 3 equations. We're actually going to set up a system of equations. So the first one we're going to have is where this blue line and this purple line intersect, this dot here. So what we're going to want to do to set up the first system of equations is we're going to set the purple equation and this blue equation equal to each other. Because we know that where these two lines intersect, the two equations are equal to each other. So we're going to find those values there. So let's set this equation, minus 2 over 3 times x plus 4. We're going to set that equal to this equation. We have minus 3x plus 6. We're going to go ahead and solve for x, and then we can plug back into either equation and solve for y. So let's go ahead and add 3x to both sides. Add 3x over here. These two terms will cancel. We can actually subtract 4 from both sides in the same step if you want. Cancel those two terms. We can rewrite 3x as 9 over 3x minus 2 over 3x. We can actually combine those fractions in the next step. 6 minus 4 is 2. This will give us 7 over 3 times x equals 2. Let's go ahead and multiply by the reciprocal. We should be very good, very familiar at solving equations here. So those two cancel, so we have x is equal to 3/7 times 2, which is 6/7. And we have a value for x. So let's go ahead and plug in this value into either one of the equations and get a value for y. Let's use this one because this one has a fraction. I like to make life easier. So we have y equals minus 3. Remember, it's an equal sign because we're looking for an exact point. We're not looking for a region. So y equals minus 3 times x, which is 6 over 7, plus 6, which equals minus 18 over 7 plus 6. We can rewrite 6 as 42 over 7. So we can combine these two fractions and we get 24 over 7. So now we have a value for y. So this point right here is defined as the point 6 over 7 and 24 over 7. So now we have the value or the exact solution for this particular point right here. And now we have two more points to find out the solutions for. So let's go ahead and make some room here. We're going to have 2 more sets of linear equations. Okay, so now we want this intersection point of the green line and the purple line. So let's go ahead and set those equal to each other. We have the green line here, which is 1 over 3x minus 1 equals, we're going to set it equal to the purple line. The intersection is where these two equations are equal to each other, or these two inequalities are equal to each other, but we're going to set them equal because that's the intersection. So minus 2 over 3x plus 4. Let's go ahead and solve this one for x. So we're going to add 2/3 to both sides. 2/3 x plus 2/3 x. These two terms cancel. We have 1/3 and 2/3 equals 3/3, or just 1. So x minus 1 equals 4. We can add 1 to both sides. These two terms will cancel, so we get x is equal to 5. So now we have a value for x. We can plug it into either equation. Let's go ahead and, well, we're going to have to deal with fractions either way, so let's go ahead and deal with this one. So we have y equals 1 over 3 times x, which is 5, minus 1. So we have 5 over 3 minus, we turn 1 into 3 over 3. We get a positive 2/3. So we have a value for x and a value for y. And this point where the green line and the purple line intersect is going to be given by the point, or by the exact solution, 5 and 2/3. All right, so we have two solutions for two of the points. Let's go ahead and find the last one, and then we can compare them by plugging them individually into our cost equation. Let's erase this right here. Okay, so the third point's right here, and this is found by setting the equations, the blue equation and the green equation, equal to each other. So we have minus 3x plus 6 is equal to 1 over 3 times x minus 1. Let's go ahead and solve this for x. So we have minus 1/3 x from both sides. These two terms will cancel. So we can turn 3 into a minus 9 over 3 minus 1 over 3. These terms both contain x. Let's go ahead and subtract 6 from both sides in the same step. So we have minus 1 and minus 6 is minus 7. Minus 9 and minus 1 is minus 10 over 3. X equals minus 7. Let's go ahead and multiply by the negative reciprocal so we can have just a positive x on the left-hand side. So minus 3 over 10. This term will cancel. So we have x equals minus 3 over 10 times minus 7 is a positive 21 over 10. And we have a value for x. So for our third point, we have x as the x value for this solution point is 21 over 10. Now we can plug it into either equation to get our y value. Let's plug it into the y equation. So we have y equals minus 3 times x, which is 21 over 10, plugging it in for x, plus 6. This will give us a minus 63 over 10, plus, let's rewrite 6 as 60 over 10 so we can combine these two fractions. And the answer is minus 3 over 10. That's our y value, minus 3/10, which makes sense because just intersection just below the x-axis. Okay, so we have our three solutions for our three corner points. All right, now what we're going to do is we're going to plug them in one at a time to get a value for all three. Let's go ahead and erase this. All right, so one at a time, we're going to plug in all three of these values into our cost formula and see which one gives the maximum and minimum value. All right, so let's go ahead and do that. So we have z equals. Let's go ahead and use this point first. This is the point right here where the purple and blue line intersect. So we have 5x, we have x, we have 6 over 7, plus 2y, y is 24 over 7. This will give us 30 over 7 plus 48 over 7, which will give us 78 over 7. Okay, so for this one gives us 78 over 7, or approximately, just approximately 10, about 10.1. So this is our first one. Let's look at the next one. Let's get a different color here. Let's use this point. So we have z equals 5 times x, x is 5, plus 2y, y is 2/3. We're talking about the solution point where the green and the purple line intersect. This is going to give us 25 plus 4/3. We can call 25 75 over 3 plus 4/3. That's a 4, which will give us 79 over 3. 79 over 3 is approximately 26.3. Okay, so that's actually much higher than 10. All right, let's go ahead and find the third value. So z equals 5x, x is 21 over 10. We're checking this third solution point, this third intersection right here where the blue and the green line intersect, plus 2y, y is minus 3 over 10. And let's go ahead and solve. So we have 5 times 21. Actually, we can simplify this a little bit. Factor a 5 out of the top, or 5 and 10. So we have 21 over 2. So 21 over 2 minus, we can factor a 2 out of the 2 and the 10. So we have a minus 3 over 5. we can cross multiply to get this answer, which will yield 99 over 10, which is approximately 9.9. Okay, so we have three values for these 3 points. What does all that mean? Well, like I said earlier, somebody proved that the extreme values of the optimization equation, which is the cost value equation, this is the optimization equation, and they proved that the extreme values will always be on the intersections or the corners of the feasibility region. So we plugged these values into our optimization equation, and we found these maximum and minimum values. So we just have to realize that what we have. So we're going to go ahead and label these as maximum and minimum values. We have a maximum value, our maximum value of 26.3. Maximum value of 26.3 is occurring at the point 5 and 2 over 3. So 5 and 2 over 3, this is our maximum value. And we also have a minimum value. Remember, we wanted the maximum and minimum value. We have a minimum of 9.9 here, approximately 9.9. And that occurs at the point 21 over 10 and minus 3 over 10. So this is our minimum value here. Okay, so this is called linear programming, and what we did is we took an optimization equation, which a lot of times is referred to as a cost equation. We were given these constraints, and we found a feasibility region, which we used that to find the maximum values and the minimum values at these given points. So you can say that if this is a cost equation, we're talking about labor and materials, well, we have a maximum profit of $26.30 when we're using, if X is labor and Y is materials, we're using 5 units of labor and 2/3 units of materials. Now, this doesn't make sense until we actually look at it on paper or actually in a real-world situation, but we'll actually be looking at a few applications in the next few sections. So look over this and just understand how we did it, and we'll see you in the next video.